All right. So what we had done on Monday was for the neural field model of the following form. So u sub t equals minus u plus the integral from 0 to pi w of x minus y. Put a bar over that, u of y t dy. Okay, we had first of all showed that a homogeneous solution exists, okay, where u of xt is equal to just some constant. And in that case, u bar is equal to f of u bar times the integral from 0 to pi of w bar of y dy, okay? And for w bar x minus y, well, let me just call this w of x, right? So this is just your kernel in the neural field model that represents the interactions between neurons. If we take this to be just a sum of even Fourier modes, or just cosines, wn cosine 2nx, where wn is in R, okay? Then this becomes u bar equals w0 f of u bar, okay? So we can sort of plot this, right? So if I plot as a function of u bar, I just plot u bar, and then in particular for f of u bar is equal to this nonlinearity 1 over 1 plus e to the minus u minus kappa. Then we get something like this, right? So where we have some intersection here, some intersection here, and some intersection here. So this is our w0 of f of u bar here, okay? And in particular, if we take, for instance, this to be shallower and shallower, so as eta gets small, okay, this will sort of flatten out, okay? And we'll have something more like this and this. So this will be our w0 f of u bar, and this is our this here is our u bar here, okay? So we would only have a single intersection point here. And the idea is that we're gonna start within this regime, and we're gonna steepen this nonlinearity, and then you're gonna get, you know, some bifurcation in the number of homogeneous fixed points. But you can also get a bifurcation in the spatially patterned states, right? So this equation, right, it has spatially constant, time constant solutions. We were looking into essentially the emergence of spatially varying but still time constant solution, okay? So to see how bump solutions emerge from this flat solution, okay, apply perturbation theory, okay? And so we took that, we assume u of xt is equal to u bar plus epsilon u of x e to the lambda t. And after a bit of work, we found that we have an eigenvalue problem. Lambda u of x is equal to L u of x, where L of u is equal to minus u plus integral from 0 to pi w bar w x minus y f prime of u bar and then u y dy. Okay, so this is a linear operator. Okay, and just like a matrix, it has eigenvalues. Okay, but as we know from like Sturm-Liouville theory, these linear operators often have an infinite set of eigenvalues and eigenfunctions that correspond to that. Okay, and what we found is that LU, okay, has eigen solutions given by lambda n is equal to -1 plus f prime u bar wn over 2, where n can be all the integers, and our corresponding eigen solutions are going to be un equals cosine 2nx and sine 2nx. Okay, so both of these eigen solutions share the same eigenvalue. Okay, and you can plug that in and show that. Okay, now our bifurcation parameter, and bifurcation is just basically where if we change some parameter of the system, the fundamental nature of our solutions change, and that could be the stability of solutions, or it could be the emergence of an entirely new solution that we didn't have before. And in this case, our homogeneous flat solution is going to destabilize, and it's going to lead to pattern formation. It's going to lead to this bump. And so our bifurcation parameter is mu equals f prime u bar over 2. Okay, and so that means we're going to rewrite lambda n equals -1 plus just mu wn. Okay, and if we look back at f, so I'm going to go back to this slide, there's a number of ways that we could change mu, right? We could change eta, which is basically changing the gain of this nonlinearity. We can make it steeper. We can make the nonlinearity steeper. If you make eta very, very large, this behaves almost like a step function. If you make eta really small, it's more like a, sort of a flattish sort of linear type function. And we can also change kappa, which would change the threshold of this function. So that would be like shifting the function, left and right. Okay. We don't so much care the details of how we do that, but the assumption is that we can change mu and it will change this value right here. Okay. So for mu small enough, what we have is lambda n is less than 0 for all n, and the fixed point is stable. Okay. As mu increases through some mu c, the equilibrium destabilizes. Okay. All right. And in particular, this is by the largest Fourier component. Okay. And in particular, here we'll suppose that W1 is equal to the max over n of Wn. Okay. And this would be like, for instance, you have a weight function, W bar, and it looks something like this. Okay. It's dominated by the first eigenmode, which is your just simple cosine, right? So cosine of 2x in this case, okay? And this just says that, you know, neurons that are close together are going to excite one another, and they could be close to, you remember this is a periodic network, and so over here is close as well. And then neurons that are far away from each other, they suppress one another, okay? This is very similar to the type of mechanism that causes pattern formation in what are called reaction diffusion equations, where you know, chemicals that are diffusing around each other, the ones that don't diffuse very far tend to activate each other, and the ones that diffuse farther tend to inhibit one another. These sort of activator-inhibitor systems. And so this is sort of the integral differential equation analog of that, okay? And so the idea then is that if lambda is greater than 1 over W1, okay, then for some lambda n, we have that lambda n is greater than 0, okay, and the excited modes grow, okay? And so for sure, we know that n equals 1 will be the most excited mode in this case, okay? And so if we do something like make a plot of lambda n as a function of n in this case, we have 0, 1, 2, 3, 4, 5. And we can plot this. Maybe we have the first eigenmode is excited, and then the second eigenmode is excited, but maybe the third eigenmode and the fourth eigenmode and the fifth eigenmode are not, right? So this all depends on our choice of weight function, but in this case, this is our max eigenvalue. And so the way that this pattern is going to look is going to depend on which mode gets excited the most, okay? And this is common in pattern formation, that you look for instabilities, and the eigenmode that it has the sort of largest positive real part is going to be the one that dominates the instability, okay? This is sort of like in phase plane analysis, right? If you have a point that's unstable, right? The eigenvector associated with the largest positive eigenvalue is going to tend to be where your trajectories shoot off in that direction, okay? You also see this with like saddles, right? Is that sort of only along the unstable direction is where the trajectories tend to go as time goes to infinity. Okay, so that's the linear analysis. Now we want to do nonlinear analysis. So how do we do that? Well, we need an amplitude equation, and this should sound familiar. To what we did for resonance systems, because this is sort of a way of preventing resonance, essentially. We want a bounded solution. And the idea is that we want a bounded solution to equations in our epsilon hierarchy of expanded equations. And linear stability analysis is going to break down for large amplitude activity, okay? So we need some non-linear analysis near the bifurcation, right? So we're going to assume that mu is close to that critical point. What's mu c? Mu c is just that value, right? In this case, it's 1 over W1 that leads to instability, okay? So if we're close to there, then that means that this is going to be small, some small deviation from mu c. And of course, like with everything, epsilon is small, okay? So if delta mu equals order 1, okay, then we have mu minus mu c is equal to order epsilon, okay? So what we'll do is we'll expand in epsilon, and we get that f of u minus f of u bar is equal to mu times u minus u bar plus something I'll call G2, u minus u bar squared plus G3, u minus u bar cubed plus order u minus u bar to the 4th terms, okay? And I'm not going to write these down because, well, for now, I don't want to muddy the waters, but essentially you can do this by plugging in an expansion and obtaining essentially the coefficients that you get from Taylor's series. Okay. So we're going to assume that u equals u bar. But then since we're close to a bifurcation, we could pick some arbitrary epsilon scaling, okay? It turns out the epsilon scaling that leads to the pairing up of the most terms is an expansion in epsilon to the 1/2, okay? We could go through that, okay? But, it's the kind of thing that we've done before, and I want to make sure that we sort of get to the result, okay? So this is our expansion of u, and we're going to ask essentially what happens to the first, second, and third order corrections around this bifurcation. Okay. Now the dominant temporal behavior beyond the bifurcation is, as we might expect, slow growth of the excited mode. And in our particular example, we know that that's the mode associated with W1, right? So n equals 1, or cosine of 2x, and also sine of 2x, right? So if we want to express those eigenmodes together, we can say it's going to be cosine of 2x with some phase shift, right? Because we can take the cosine 2x and the sine 2x and basically scale them in any way we want and get this phase shift. So we're going to allow for some phase shift because of the translation symmetry of the system, okay? And according to e to the epsilon delta mu t, okay? And this motivates the slow time scale tau equals epsilon t, okay? Now remember, we're close to the bifurcation, so that means the eigenvalue is only going to be of order epsilon, okay? So that means that these changes will happen slow, so that's why we can use method of multiple scales now, okay? So we have a slow time scale, we have this expansion in mu1, okay? We can sub this into the neural field equation. And we get some expansion, right? So we get dt plus epsilon d tau, mu bar plus square root of epsilon u1 plus epsilon u2 plus epsilon 3/2 u3 plus so on and so on is equal to minus u bar plus square root of epsilon u1 plus epsilon u2 plus epsilon to the 3/2 u3, okay, plus integral from 0 to pi w bar x minus y f of u bar dy plus 2 integral from 0 to pi w bar x minus y mu c plus epsilon delta mu times all this square root of epsilon u1 plus epsilon u2 plus epsilon to the 3/2 u3, okay? Integral from 0 to pi w bar x minus y. Now the squared terms, right? Square root of 3, square root of epsilon u1, epsilon u2 plus epsilon to the 3/2 u3 squared dy. And then finally the cubic terms, integral from 0 to pi w bar x minus y g3 square root of epsilon u1, epsilon u2 plus epsilon 3/2 u3, so on and so on, dy. Okay. So that whole mess, right? That's just everything now plugged into our neural field equation. Okay. Now, yeah, this G2 and this G3, right? They're just going to depend on the particular form of our sigmoid function, right? So they're going to depend on eta and kappa, right? So we assume we can get that form. Okay, we won't worry about defining that. Now remember, before we had defined this linear operator LU that's equal to minus u plus 2 mu c integral from 0 to pi w bar x minus y uy dy, and this is equal to, in shorthand, u plus 2 mu c w convolved with u, okay? And this is a convolution, okay? Now that linear operator is just going to show up over and over again in our hierarchy, right? So if I take this big mess and I start peeling off order 1, order epsilon to the 1/2, order epsilon to the 1, order epsilon to the 3/2, and so on, okay? The homogeneous part of my equation is just going to repeatedly be this linear operator, okay? And that shouldn't be that surprising, because if you remember from method of multiple scales that we've dealt with before, that happens there, right? You always have this this linear part that's just passing through the linear operator that you get by linearizing, right? So at each order, you're going to have, u1, u2, u3, and so on being acted on by your linear operator, okay? And so our hierarchy now at order 1 is going to be u bar equals w0 f of u bar, okay? That's just the equation we had before. That defines our u bar. We don't really need to worry anymore about that equation. At linear order, we have almost the equation that we had before, but it's no longer an eigen problem, okay? Because we have this slow time scale that we've introduced, and also we're close to the bifurcation, so the eigenvalue is small enough that it gets kicked up to the next order. Okay. At order epsilon, we have LU2 is equal to minus G2 W convolved with U2 squared, and this is equal to something we'll call V2, which is just our inhomogeneity on the right-hand side. And then finally, order epsilon to the 3/2 is going to be LU3 is equal to dA1 d tau minus 2 delta mu W convolved with A1, and I'll define A1 in a little bit, 2 G2 W convolved with A1, A2 minus G3, W convolved with A1. And we'll call this whole thing V3. Okay. And in particular, order epsilon to the 1/2 equation has solutions that are given by A1 is equal to Z of tau e to the 2ix plus Z bar of tau e to the minus 2ix. Okay. So this is our linear operator here, right? It has solutions whose modes are given by this by the dominant eigenmode, right? E to the 2ix here. But because it doesn't involve any differentiation or any tau dependent terms here, we know that the prefactors can depend on tau. Okay. So this should be very reminiscent of things that we've done before in method of multiple scales. Okay. And we're going to get, a similar homogeneous solution at order 2, or I guess order epsilon, excuse me. But order epsilon to the 3/2 basically is where we should expect to find an amplitude equation. Okay. And if you remember when we've derived amplitude equations in the past, that's where our sort of slow time scale emerges. Okay. And we get some restriction that allows us to take this in the homogeneous right-hand side and turn it into an equation, okay, by basically eliminating the secular terms from this equation, okay? So, so we need a solvability condition, and that's what's given by the Fredholm alternative, that basically says this right-hand side needs to be orthogonal to the null space of the adjoint of this linear operator, okay? That's basically what we did before for resonance conditions, okay, but we just didn't call it that in the case of the resonance conditions, but that's essentially what you're doing, okay?
In the order epsilon equation, is it supposed to be a U1 squared or a U2 squared on the right-hand side?
Yeah, that should be a U1, thanks.
Okay.
Yeah, because that should only depend on the lower order stuff, yeah.
Okay.
Yeah, thanks. Okay, so to obtain dynamics of Z, okay, derive solvability of order epsilon 3/2 equation, okay? So notice, right, that all the higher order equations have the form LUN is equal to VN, and that just depends on U bar, U1, all the way up to UN minus 1, okay? We're going to define the inner product as 1 over pi integral from 0 to pi U bar x V of x dx, okay? Now, integration by parts can be used to show that L is self-adjoint, right? And if we look at L, right, where's L here, right? We just have a minus U, and then we have this integral term, okay? And due to the symmetry of this kernel here, okay, it's not too much work basically to show that you have a self-adjoint operator here, okay? So L is equal to its own adjoint, okay? So for U tilde is equal to E to the plus or minus 2ix, okay? We have that U tilde LU tilde is equal to L U tilde U tilde, okay? And this should be equal to 0, okay? Now, since LUN is equal to VN, and U tilde spans the null space of L, which is its own adjoint, okay? Then we need U tilde Vn equal to 0 for all n greater than or equal to 2, okay, for solvability. Okay. Now it turns out you can show that order epsilon solvability, okay, U tilde V2 equals 0. We can show this is automatic, satisfied, okay? So if you go back to the order epsilon equation, it's here. If I integrate this right-hand side against e to the 2ix, okay, everything cancels out because this part here, right, is going to pick out an eigenmode that's not the 2ix eigenmode, okay? And so it's going to be orthogonal to that, and everything's going to go away, okay? Now, at order epsilon to the 3-habs, that's where we have to enforce solvability, and we get something non-trivial. So we take U tilde, and we integrate it against the right-hand side of that, okay? So we get dt A1 delta mu W convolved with U1 is equal to G3 U tilde W convolved with U1 cubed plus 2G2 U tilde W convolved with U1 U2. Okay. Now, if we take U tilde equal e to the 2ix, then we have that e to the 2ix convolved with dt U1. Sorry, I'm writing these A's and the U's should be the same in this case. Okay. So d tau U1 here, d tau U1. This is equal to 1 over pi integral from 0 to pi e to the minus 2ix dz d tau e to the 2ix plus dz bar d tau e to the minus 2ix dx, okay? And all that's just equal to dz d tau, okay? And then the right-hand side is messy, right? So to deal with the convolution, note that for any b of x, okay, since w bar of x is even, then we have the following result, okay, that I'll derive and make sure everyone's caught up here. Okay, we have the following result. So e to the 2ix w convolved with b is equal to w convolved with e to the 2ix b, okay? which we can write as 1 over pi, integral from 0 to pi, integral from 0 to pi, w x minus y, e to the minus 2iy, dy, b of x, dx, okay? And plugging in expression for w bar, I guess in this case, and integrating, what we end up with at the end of the day is that we just have 1 over pi integral from 0 to pi w1 e to the minus 2ix e of x dx, which is w1 e to the 2ix b. Okay, so the only thing that happens from this is that just the w1 mode is what gets represented, right? Because this is the w1 mode here. Okay, so you're just picking out that part of the weight function. Okay, so if we set w1 equal to mu c to the minus 1, because it is in our particular case, then we have that e to the 2ix delta mu w star u1, okay, is going to be equal to mu c to the minus 1 delta mu z, okay? And we have that e to the 2ix w star u1 cubed is equal to, after a bit of work, 3 mu c to the minus 1 z squared z, okay? So basically that integrating against that eigenmode is picking out just that component of the weight function, okay? And then also the, whether we're cubing or we just have the linear part here determines the amplitude of your U1 solution that gets represented, okay? Now we can determine U2 from the order epsilon equation, and we get that LU2, or I'll write this as minus LU2, is equal to U2 minus mu c integral from 0 to pi w bar x minus y U2y dy. This is equal to G2 integral from 0 to pi w bar x minus y u1 squared y dy, okay? And if we compute what this part is, we get just G2 to z squared w0 plus z squared w2 e to the 4ix plus z bar squared w2 e to the minus 4ix, okay? So just by squaring this part, right, we get these 4 different Fourier modes, okay? And this has a solution given by u2 of x is equal to g2 z squared w2 over 1 minus mu c w2 e to the 4ix plus g2 z bar squared w2 over 1 minus mu c w2 e to the minus 4ix plus g2 amplitude z squared w0 over 1 minus mu c w0. And I'm going to call that A0. I'm going to call this A minus, and I'm going to call this A plus, okay? And you also have a part of the solution that's like zeta times u1 of c. Okay. So so we're almost there. Okay. So so this is your u2. You just need to solve for u2 just like you did in the homework problems in order to now plug it into the order epsilon 3/2 equations. Okay. So that means that I can finally compute this. E to the 2ix w convolved with u1, u2. Okay. And we get at the end of the day that this is equal to z squared g2 mu c to the -1 w2 over 1 minus mu c w2 plus 2 w0 over 1 minus mu c w0. Okay. And if we sub this into mu tilde dt u1 minus delta mu w star u1 equals g3 u tilde w star u1 cubed plus 2g2 u tilde w star u1 u2. Okay. We obtain, finally at long last, what's called the Stewart-Landau equation, which arises in pattern forming systems, amplitude equations for pattern forming systems. Okay. And that's just dz d tau equals z delta mu minus some coefficient, which I'll call capital lambda amplitude of z squared. Okay. Where in our case, okay, this big lambda is equal to minus 3g3 minus 2g2 squared w2 over 1 minus mu c w2 plus 2 w0 over 1 minus mu w0. Okay. And we also had to do some rescaling tau by mu c. Okay. Well, so what? So essentially, we've taken this complicated neural field equation and we've said, not only do I know that a pattern emerges beyond this bifurcation, but I can track its dynamics, okay, to some cubic order. And in particular, this is just, you know, a dynamical system that we can analyze using those techniques, okay? It has steady states, z equals 0, and z equals the square root of delta mu lambda e to the I theta in this case. And the stability of solutions for z equals 0 is lambda equals delta mu. That should be no surprise. So it's unstable if delta mu is positive, which means we pushed ourselves past the bifurcation point. Okay. For the other more interesting solution, right? For z equals this delta mu over lambda e to the I theta, okay? Lambda equals minus delta mu e to the 2I theta minus phi, okay? Where z equals sort of this z0 plus epsilon z1, okay? E to the I phi, e to the lambda tau, okay? This is your perturbation, okay? So depending on how you perturb this solution, you're going to get a different eigenvalue, right? So you have a continuum of eigenvalues, okay? So if theta minus phi has magnitude pi over 2, okay, then that lambda equals 0, okay? And it basically means it's marginally stable to shifts, okay? So if you perturb this fixed point sort of tangent to the ring that it sits on, okay, then it does not relax back. But if you perturb in any other direction, you relax back to the fixed point that you were at, okay? I think this is easier to understand if I draw a picture, and then I'm done, okay? So what we have then is in this plane, right? We have the real part of z, we have the imaginary part of z, okay? Here we have our quiet state, basically z equals 0, and we have this ring of stable fixed points for delta mu is greater than 0, okay? This is our ring of stable bumps, okay? And basically, if I pick a bump along here, if I perturb it this direction, I have marginal stability, which means I can shift that bump around anywhere I like. If I perturb off in this direction, it's stable, basically to making the bump smaller or bigger in this direction, okay? So if I draw this out, right, u as a function of x, I'm going to have, I guess this is, I'll take this to be 0 and this to be pi here. And I have a bump here, and I can shift it left or right, and it's marginally stable, right? This peak here represents this theta, okay? That would be the angle of that z variable, right? Of the amplitude, okay? But it's going to be stable to expansions and contractions, which means that if you take this bump now and you expand it or contract it, right, it'll relax back over time, okay? So just to sum up, okay, what have we done? We've taken the neural field model. We have identified pattern forming solutions that emerge as you change the shape of the nonlinearity in the model, okay? The form of those pattern forming solutions is going to be determined by the dominant eigenmodes of your weight function, okay? So it's going to reveal basically the synaptic connectivity of the model through the bumps that emerge. And people have used this to help identify properties of visual processing, the origin of visual hallucinations, lots of different applications, particularly in sort of sensory processing in the brain, okay? The equation that you get when you perform this nonlinear analysis gives a very detailed picture of what emerges beyond this bifurcation. It's basically this ring of fixed points, okay, that are marginally stable to perturbations. And this kind of structure in a system is very useful not only for sensory processing, but also for memory, right? If you have something like this is actually called a ring attractor in a dynamical system, you can store information in it, right? So depending on the initial condition of the system, it'll relax to a particular point along this ring, and it will remember something about the initial condition that you presented to this system. On Friday, we'll talk about what happens if you add noise to this type of model and how that starts to degrade memory of that initial condition and what that says about short-term memory in the brain. Okay, so I know I was pretty quick through some of that. Are there any questions about this before we conclude for today? Right. Well, thanks, and I'll see you all on Friday. Have a good rest of your day.
Thanks, Zach.